Welcome to ARC308, the serverless company using AWS Lambda. My name is Vyom Nagrani. I am a senior product manager with the AWS Lambda team. I'm joined here today by Jay, who will be also co-presenting with me. And we'll be talking about streamlining architectures with AWS. So what to expect from this session? I'll do a quick overview of the evolution of cloud compute towards serverless and explain what serverless is and how that works. I'll do a quick walkthrough into what AWS Lambda is and some of the features and functionalities of the product. From there, we'll go into how to build a serverless data processing architecture using AWS Lambda. And we'll have an example of a live video processing architecture as a special case of this, which Jay will present. After that, given this is an architecture talk, I want to go deep into real-time data processing architecture patterns and talk about what different architectures you could build using AWS Lambda. I want to leave you all with a few tips and tricks of how you could use AWS Lambda to build small applications or large applications, depending on what your use cases are. So let's talk about the evolution of cloud compute. So everybody knows the benefits of the public cloud. And the way it works is that there is this infrastructure on which you have your instances running. And these instances may be EC2 instances or any virtual machines. And what you are running on top of these instances is your application code. So what's happening here is that there's a lot of overhead which you have to manage for running the application code. If what you worry about running is the application, you still have to also worry about managing the underlying instances, the configuration, the setup, the scalability, the deployment. And we heard from customers that this is something that developers don't really want to focus on. They want to focus their efforts on the application development. So in this era came the whole concept of containers. And containers actually made life a lot easier. So what containers did is on these instances, you first deploy the containers. And then because the containers are very lightweight, it's very easy to deploy these things. It's very easy to manage the functionality of these containers. And then on these containers is where you run your actual application code. And you can decide what you really want to do here, whether you want to use containers for individual functions or individual applications, or you want to use containers for segregating your applications, where one application should talk to another one, but the third one should be an independent one. Or you're using containers only for deployment, where the whole application still works the exact way it used to before, but because the containers are much easier to deploy, you package everything into a container and then use the tools available for container deployment and management. But if you really think of it, while this makes life a lot easier, as our CTO mentioned, no servers is easier to manage than no servers. All of this still is an overhead for application developers. It's easier, but what you really care about here is the application code. So imagine an environment where you have the infrastructure and the application code is just running there, and you don't have to worry about what's underneath, what's below there. You don't care about what else is running on the same infrastructure, the way you don't care about what else is on Amazon S3 buckets. All you care about is that when your application needs to scale, there should be room for your application. And then the things like security, scalability, management, deployment, all of these are taken care of by the service. That's effectively what AWS Lambda is. AWS Lambda was built on these principles. So the AWS Lambda is a serverless, event-driven service. What event-driven means here is that the infrastructure beneath the containers is automatically scaled up and down on your behalf by the system whenever there is an event that needs to be processed. This makes Lambda very useful to build microservices without the servers. To talk about a few benefits of AWS Lambda, one, as we mentioned, it's serverless, which means all of the infrastructure management, all of the deployment pane, all of the work that you need to do to make sure your application works in a scalable, reliable, durable manner is taken care of by the system. Second is event-driven scale. The benefit of Lambda is that if there's going to be an infrastructure management behind the scenes for each event, this means that Lambda will automatically match the incoming rate of events for you. And no matter what that scale of events is, there'll always be just the right amount of capacity, just the right amount of number of functions to execute those events. This takes away all the pain of ever being under-provisioned or over-provisioned, because there is no provisioning. Your event is what triggers the system to provision the capacity just to process that event. The third is that Lambda offers sub-second billing, which means that you don't have to worry about how long your application runs or what you're going to do when the application is not running, because you don't have to pay for it when it's not running. If an individual event takes 16.7 seconds to process, you just pay for 16.7 seconds. You don't have to worry about the idle time where you're waiting for something to happen. So effectively, now with these two things, you are getting 100% utilization, and your application is tracking exactly only the amount of time that it's actually running. Talk of a few capabilities about Lambda. The way Lambda works is you just bring your own code. We support Node.js and Java. And as of today morning, for those of you who heard the announcements, we also support Python 2.7. The goal of Lambda here is to make it a completely polyglot service, which means we want it to be a system which supports multiple languages. So for users, you don't really have to learn a new language. The language which you already are comfortable in, just bring that code. It's stock Node, it's stock Python. The code which you already have running, just port that over to a Lambda function, and you're good to go. We have a very simple resource model. So unlike a lot of infrastructure provisioning, where you have to think of what memory and what CPUs and what exact instance type or what configuration you want, so there's only one thing which you need to configure for a Lambda function, and that's the amount of memory. And think of that as a power level for the Lambda function. We allocate CPU and I/O proportional to the memory that you allocate, which means a 256 MB function will have twice the CPU as much as a 128 MB function. So it makes it very easy for developers to decide how much power levels do they want. And in most cases, because the pricing is in GB seconds, it's a multiplier of how much power you provision times how long it ran. For all CPU and memory-bound applications, provisioning more is going to make your system run faster, so it's going to take fewer seconds. So it doesn't really matter in terms of your economics, and you might as well just set the highest memory that you want so that you finish processing your events faster. We have flexible invocation paths for Lambda, which means that you can trigger Lambda functions or invoke Lambda functions either synchronously or asynchronously. You can invoke them either directly from the CLI or through an API, or you can hook up Lambda functions to process existing AWS service events. And what this helps with is that you no longer have to build a lot of those connections and pipelines to transfer the data from one service to another. Lambda will automatically invoke whenever there's some new data to compute. Lambda uses IAM roles, or identity access management roles, under the hoods. So you can have very fine-grained and granular permissions that you can grant to your Lambda function. You can say that my function should only be able to talk to this S3 bucket in this region. And it can make it very effective to control what your Lambda function can do. And also, we heard in today's announcements that Lambda functions can now also talk to resources behind your VPCs. That feature is coming soon, which will give you even more control over what your Lambda function can and cannot do. For authoring of Lambda functions, you can author functions the same way you would author them in your own environment. You can make use of threads and processes and forks, and you can bring in all of your packaged libraries and binaries. You can even make use of all of the programming constructs which you are very used to in your standard environments. For deployment, we have different deployment options. You can either edit directly inside the AWS console, or you can upload a zip file which has all of the package dependencies which you need. Plus, we are trying to expand our partner ecosystem in this space to get in more plugins and more controls so that the existing tools which you have can easily be plugged in for deployment. We use Amazon CloudWatch for monitoring and logging. So we have lots of metrics which we publish to Amazon CloudWatch, as well as all of the Lambda system and user logs go to CloudWatch logs. But even in this space, we are trying to be more open, and we have different partners in which who you can use for logging of Lambda functions. The thing here to note is that Lambda functions are stateless, and this allows us to horizontally scale out very quickly to match the rate of incoming requests. But this also means that you can't really log into the box and try to SSH into what's going on, because it's a stateless function. We're building out the partner ecosystem, as we said. We have lots of partners for deployment, for extension of what Lambda can do, and for logging. And this list we are planning to grow over time. If you go to the AWS Lambda console, we have a concept called blueprints, which is basically a sample template which you can quickly get started with. As of today, we now have 3 partner blueprints, so you can also quickly get hooked up into what the partner ecosystem benefits can bring you. So that's about Lambda, but let's talk about what architecture patterns, how architecture patterns will be different because of AWS Lambda. So let's take this old world the scenario where you're trying to process some data with servers. And that source of data could be anything. It could be an S3 objects, it could be Kinesis records, it could be DynamoDB tables. Think of anything where you are bringing data to the cloud, and you want to process that data. So you have this one server, right? But then one is not enough. So you're going to have multiple servers to process your load, and you're going to have things across AZs. Now that you have multiple servers, it can't directly talk to the source, so you're going to have a queue in between. And the Lambda and the servers will actually pull the data off the queue. If you have queues, then you need to have something which actually listens to the event source and publishes to the queue. And that listeners and pollers also need to be a separate fleet, because you don't want that to be in a single AZ. You want that to be auto-scaled. And the fleet of workers that you have also need to go through a whole range of auto-scaling, depending on how much load you have on the system. You're going to have things like cross-AZ replication, so that if one AZ goes down, if in the worst-case scenario, you want your application to still persist. You're going to have to think of load balancing to distribute the traffic across all of these workers. So what started off as a very simple application, I want to process data, is now this whole complicated setup which you now need to manage. And remember, as a developer, what you really care about is the application code that's running on these servers. Everything else on this screen is an overhead for you. So let's look at how that architecture would be different in a serverless environment. You have the same source of data. You attach that to a Lambda function, and that's it. Lambda does the listening, the polling, the queuing, the auto-scaling, the load balancing, and all of that is done by the system. All you have to do is bring that application code to Lambda and let Lambda handle the rest of it. To give an example of what I just talked about, I'd like to invite Jay on stage to give us a quick intro.
This one's full. That's weird. OK. It just switched to the other laptop. While we're pulling those slides back up, my name is Jay Sandhouse. I'm the CTO of Play on Sports. Play on Sports is a high school sports media company. We stream live video of high school sports, a lot of it, about 50,000 events a year. We stream that video whenever high school students are playing sports or doing other events, everything from morning announcements to football games on a Friday night when football is played in America. One of the things we offer to schools are tools to produce a professional streaming broadcast with no real expertise or experience in streaming or broadcast production, so students can learn about that in school. It's really a broadcast production studio shrunk down to a box. We have a slightly different use case than a typical media company. Typically, a media company would have a small number of live streams or live events and a very large audience for each one of those events. Because we're giving these tools to schools all over the country, we have a different use case. We will have a lot of live events going on at the same time, so a high number of streams coming in and a slightly smaller audience for each one of those. In aggregate, our peak hours maybe would look like about 300 live events all going on at the same time with perhaps 20,000 people at any given minute watching those events. So we have a particular challenge. We need to transcode and work with a lot of live video all at once. So we need to be able to take all of those 300 streams, perform quality of service, and really get those out to a lot of people all at the same time. This thing is still going the wrong way. All right, so our architecture historically for doing this has been, looks probably like what you would expect a video processing architecture to look like. We take RTMP video, that's flash video encoded in the field. We bring that back through our CDN, and then we have various pools of servers performing work on that video. There's a pool of servers that's taking that video and changing it from RTMP to something called HLS, that stands for HTTP live streaming. It's what video has to look like to work on your iPhone and some other mobile devices. That's very network intensive, but not very CPU intensive. We have a whole other pool of servers that's taking that video and transcoding it. Transcoding it means taking a high bitrate stream and turning that into lower bitrate streams, so people who are bandwidth constrained for whatever reason are able to watch that video. That's very CPU intensive as well as network intensive. We have a whole other set of servers that are recording that video, writing it to disk, and making it available for an on-demand workflow that takes over when the live streaming video event is done. And each one of those pools of servers has to be managed and scaled and has all the traditional challenges you'd have with managing something like that. There are a handful of other services around this to actually manage that video. So in total, there are probably 5 different pools of servers that are running at any given time. So one of the things that we really want to do is move away from RTMP or flash video to HLS video from the source. And HLS video is very HTTP friendly. And if we can move to a model where we're just streaming HLS segments instead of RTMP segments, it'll still be live. It'll still look like live video to the end user, but we'll get a lot of benefits from doing that. The first is we can ideally minimize our operational overhead. We're a startup, small company. We have a very small ops team. Most of that work falls onto our development team. We don't want to spend a lot of time on operations. We also want to add features that are hard for us to add right now. So it's very expensive to do adaptive bitrate streaming because it's CPU intensive, and that really adds up when you're doing 300 events at the same time. So with HLS, there may be a way that we can do that less expensively. It's also really important for us to add features like mid-roll advertising because our audience is watching our content for hours. And right now, we can only run ads at the beginning of that experience when it starts. We obviously want to minimize expense. We want a cleaner workflow if we can have it, getting back to ops. And possibly most importantly, we really want to keep our precious development resources focused on video quality and the consumer experience. We don't want to be spending a lot of time massaging the process. We really want to focus on the domain-specific issue. So we're moving from the server-based architecture I showed you a minute ago to a new architecture based on Lambda. And this is something that we are testing and using today. This isn't something that we're planning to go to in the future. This is something that we've actually built out and we're trying now. And so in this new architecture, what happens is out in the field where the video is being encoded live, it's just written to disk in 10-second chunks, about 10-second chunks. And those pieces are then pushed up through CloudFront to S3. And when they arrive in S3 in a bucket, that causes a trigger to be fired that notifies Lambda that there's now a new piece of video to process. From that point, we then have a single Lambda function that listens for that notification and then fans out to what are right now 6 additional Lambda functions that pick up that video and perform different tasks, transcode it to a different bit rate, perform quality of service analysis on it, make a thumbnail from that video, and ultimately move it to an external bucket where it can be served to consumers to view in a live experience. Those Lambda functions, we have 6 of them here right now. One of the great things about this architecture is as we decide we want to process the video in a new way, we can just add an additional Lambda function. There's no need to stand up a whole new pool of servers, which is what we did in the past when we had a new function or wanted a different capability and didn't want to impact our production environment. We can just add another function. So if there's, for example, right now it's challenging for us to support some Android devices where there may not be a lot of those devices out there, and it's not really cost effective for us to have a whole new transcode, which might be very CPU and cost intensive, just to handle those devices. With Lambda, what I hope we can do is we grow this architecture in this environment, we can identify those things, create targeted jobs for them at a much lower cost, create a better consumer experience for a larger number of people. So what have we learned so far as we're doing this? So probably the single greatest takeaway is that Lambda was very easy to use and really worked as expected. We spent almost no time working on the Lambda part of this new architecture. Everything was written in JavaScript. It looks just like you're writing a small Node application. We have a compiled binary, an application called FFmpeg, that's compiled in a separate build path, but it's just included in the zip file that Viom mentioned when we upload our actual Lambda job. It was very straightforward to create this. And so instead of spending a lot of time working on figuring out the mechanics of this and putting this together, we were able to put our energy into the domain-specific part of this problem and really focus on video. And it's allowed us not only to start building the features that I talked about a little earlier, adaptive bitrate streaming, mid-roll advertising, it's also allowed us to think about video in different ways and start think about new features we might want to add that we didn't really have necessarily the time to think about before we started this conversion process. There are still a few open questions for us. Right now, our experience has been is every Lambda job completes in about the time we would expect it to complete. As we start to run hundreds of videos through at the same time, I expect there are going to be situations where there are failures. And I don't think we've completely identified how we're going to handle those when that happens. So there's an open question about what we do when a Lambda job doesn't complete the way we expect it to. And we've also learned the method we use to fan out the Lambda jobs is probably not the best way to work. Right now, you can only have a single event notification on an S3 bucket to fire a Lambda job, a single job, when any file is written to S3. So instead of fanning out, calling one Lambda job and having that call 6 other Lambda jobs, I think we would be better off calling SNS, and then we could just subscribe to an SNS queue. So that's another approach that we want to evaluate. But the big headline is the cost savings are, at least initially, appear to be what we thought, which is about an order of magnitude over what we were doing previously. So this has really helped us accomplish our goals of getting developers focused on the domain of saving money, of adding new features, and minimizing the operations burden. So I'll turn it back over to Viom for more information about Lambda.
Thank you, Jay. So from here, let's look at some of the real-time data processing architecture patterns, and let's go deep into what an architecture would look like and what different architectures you could build using AWS Lambda. So for the first one, let's pick the one that Jay just talked about, is how you could do real-time file processing workflows with Amazon S3 and AWS Lambda. The way this would work is that whenever any S3 bucket has a new file uploaded to that, S3 recently announced something called S3 event notifications, and you can hook up a Lambda function to that S3 object notification. And once you get that notification inside of Lambda, it's an event that is generated by S3, and that event object is received inside the Lambda function, which will automatically invoke the Lambda function. There's nothing you need to do, especially once you upload the S3 bucket object. And then because it's your own code, you're bringing your own code inside the Lambda function, you can choose what you want to do with that code, with that S3 object. There are lots of applications which are unlocked because of this architecture. The one that Jay mentioned is that you are transcoding the file which you have gotten into an S3 as an event, and then putting it back to another S3 bucket. But at the same time, the same architecture can be used to create a file index on top of S3 objects. As more files are uploaded, you want to create a whole index of which files exist where, and just store the URL of that file, so that when you want to do a lookup of all the files in your S3, you don't have to do a list bucket. You can just look at this index and see which file is where, so that you know exactly which file you're looking for. And these are just two examples. But think of the different use cases you can unlock with this. If you have images which you are uploading to Amazon S3, all of those images can be thumbnailed, watermarked, processed, resized, and then stored to the other S3 buckets or served to any other endpoint. If you have video files, they could be transcoded or cut or joined with some other file, or interleave an audio to the same video file, and do such other use cases. If it's just raw data that's coming in, if you have like CSV files and you want format conversion, you can convert from CSV to JSON or any other payloads. Or you might even want to do something like an HTML to a PDF file using some of the open PDF libraries. So this is the whole architecture pattern that you're looking at, where the S3 event is triggering a Lambda function, and that Lambda function can go and do do the processing that you wanted to do on your S3 object. So Jay mentioned that he uses FFmpeg in transcoding his video applications. So let's see what that code would look like. I don't want to do a full walkthrough of the code, but let me just give you a few highlights. So I just include a few binaries or a few packages, npm modules inside the Lambda function. And I set up some variables. And all of these variables are just to say what the input file should be and what the output file should be. I also changed the name of the input and output buckets to make sure that I'm not putting the files back to the same bucket. Then I serialize the steps. Because Node is an asynchronous language, I want to have a serial execution of steps, so I use async waterfall. If you're writing something in Java or in Python, you probably don't even need to do this. So from there, I do a small series of steps. Because the event object that I get is going to have the metadata of the file, I'm going to use the metadata from that file to actually download the full object. I get that file from S3. I write that file to the local disk. The FFmpeg library that I have, which isn't, I also include in the same zip file that has the Lambda function. And now I can execute that as FFmpeg as an exec option, therefore forking off a process that goes and does this actual transcoding. That FFmpeg will create the output file. What I do next is I read from that output file and upload that object to the output S3 bucket. So let's see what that would look like on the console. So this is the Lambda function which I have created here. I'm calling it demo S3 video transcode. And then what will happen is that if I look at the event sources of this, I have the S3 bucket I had named as the event source of that. Sorry. Sorry, so let me start over. This is the video file that this is the Lambda function that I have created. And so in this Lambda function, if you see the event sources, I have included the S3 bucket name, my original bucket, as an event source. So what's going to happen is that whenever a file is uploaded to this bucket, as you can see, that bucket is empty right now, it's going to automatically trigger the Lambda function. The Lambda function will go and copy that image after transcoding it to a different bucket. And if you saw the code, I was transcoding from AVI files to MP4 files. So in this, I upload an AVI file. In the backend, whenever that file upload process is completed, I also had specified through the event source mapping that it should trigger the Lambda function. So as you can see, as this file gets uploaded, what will happen is that that Lambda function will be invoked, and the metadata of the object is going to get passed to the Lambda function. Lambda function will transcode it and output to the S3 bucket, to the output S3 bucket. As you can see, that file is showed up there when you refresh the page. And the benefit of this application is that while this showed how you could transcode one file, the benefit that Lambda brings to the picture is that there is no difference between having your having the one function running, the exact same source code with absolute no changes to the system anywhere would also work if instead of one file, I had uploaded 10,000 files. What would have happened is that would have gone and invoked 10,000 Lambda functions, and all of those output functions would have been put to the output bucket. So you don't have to worry about scalability here, and just with these 50, 60 odd lines of code, you built a whole transcoding application which will now process all of your S3 files in a real-time scenario and output them to another bucket. So let's look at some other types of architecture patterns. So we talked about how you could process files. But with Lambda, you can also process streams of data. Amazon Kinesis is a service which allows you to manage streaming data into the cloud. So if you have an Amazon Kinesis stream, the architecture would look something very similar, is that whenever new records are available on the stream, Lambda is going to automatically go and pick up those records for you if you set up that event source mapping. And then again, once you have that event data instead of Lambda function, you could run different types of applications on that stream of data. You could either compress that stream and push it to Amazon Redshift. We have a new service which we announced today called Firehose, which does a lot of these things for you. But if you want to have any sort of custom processing, which is not supported by the standard set of libraries available, you want to process only specific information and upload that to Redshift. Those are types of things which you can run with this application. For example, you want to say, I have my stream of data coming in, which is my metering records for my service, or it's a clickstream data, or it's a social media feed. And you don't want to upload everything. You want to upload only an aggregate of some of the information available. The information coming in is literally every record, and what you want is only every 5-minute granularity of data compressed together when you push it to Redshift for long-term archival and storage. So that application can be built very quickly using this architecture. Similarly, if you want to run some sort of auditing on your incoming stream of data, where you have all of the social media activity which you are ingesting into Redshift, but you only want to filter some specific patterns and then get notified whenever that pattern is found in the Kinesis stream, you could have that pattern match algorithm run inside the Lambda function. And whenever the match is found, it will push the notification to an S3, Amazon SNS topic. A third and similar architecture in this space is how you could build NoSQL triggers. So everybody is used to the MySQL triggers, which are available in a relational database. And that is processed on the same machine as the MySQL server. But with Amazon DynamoDB, which is a NoSQL offering, you get a similar trigger functionality in the NoSQL environment. And the benefit here is that whenever new data is available, the trigger doesn't execute on the same box. The trigger executes as a Lambda function. And therefore, you get the change record of each updated object as a Lambda on the stream, which Lambda function can read. And now, you can process a lot more inside the Lambda function because it's a very asynchronous way of doing it. Your table updates and your input and output is not going to slow down just because you have some processing going on in the background. And Lambda functions can run for all the way up to 5 minutes as of today. Plus, you can have 1.5 GB of RAM and the equivalent CPU available to you to process a lot of this information. So types of things you could do with this, you could either go and optimize the data and compress it and push it to another DynamoDB table, or you could just replicate the whole table without having any servers to manage, therefore giving you a multi-master or at least a master-slave functionality. Or again, you could aggregate a lot of these records and push it for archival to Amazon Redshift. Let's take two examples of these. One in which you have a game score as your first DynamoDB table, and you're attaching a Lambda function to it. And you want a separate table which has the top score of the day. So what you do is that inside the DynamoDB records, you just look at, is the current record larger than the top score? If it is, then update the top score table. If not, just ignore that piece of data and let the DynamoDB table have it. Second example architecture could be you are trying to build a dashboard of the metering activity which you are seeing. You could have all the live data feeding into a DynamoDB table. That will show the live view of what's going on. And the Lambda function can go and compress that data and store it to an Amazon Redshift table, so that now Redshift has the historical view or time series view of all of the information that's occurred, but it still is not as large because the data has now been compressed. One more architecture I'll show over here is how you could use Lambda as a message handler. As with the other three architectures, whenever a new message is published to an SNS topic, by now you will be familiar with this architecture, is that will trigger the Lambda function. And then depending on what that message is, you could do different things inside the Lambda function. Now, if that message is a true outreach or a mobile push notification that you are doing, you could actually customize that notification and then push it back to another SNS topic. So instead of sending the exact same message to 5,000 users, you could subscribe 10, 15 Lambda functions to that topic. Each of those Lambda functions will send that message out only to 700 to 1,000 users, but it will be a very customized message, because now Lambda can intercept that message, customize it, and then push it back. Similarly, if you are using SNS as a bus to push data inside of the cloud, which lots of customers we have seen often do, is have external services pushed to Amazon SNS, then what you could do is use AWS Lambda as a way of pushing all of those records into a Kinesis stream so that you can process that further. So if you saw the architecture patterns are pretty much similar, is that there are different services which can invoke a Lambda function, and then that Lambda function can go and run some processes in the background to execute those events or to process the data that was just flowing in. All of these are data processing architectures. The one slightly different architecture I'd like to highlight is how you could use Amazon API Gateway to process requests or API calls the same way you would process data. The difference here is that whenever Amazon API Gateway APIs are called, instead of an asynchronous push, it will be a synchronous call to the Lambda function. And what you could do is you could build a whole CRUD application, a complete stateful application, to respond to these API calls, whether you use Amazon S3 for file type of responses, or you're using a DynamoDB table for dynamic data responses. So with just these three services, you can build a complete API on top of AWS without having to ever worry about capacity or provisioning or infrastructure underneath, because all of these are managed services. API Gateway will become the front end of your application. It will do things like throttling and caching and authentication. Lambda becomes the compute engine, which does the actual processing and is the intelligent part of your application or your API. And S3 or DynamoDB are the stateful data stores, because Lambda functions are stateless. So with just three applications, now you have something which is very easily scalable. You never have to worry about, is this going to match to my incoming rate of requests or not? You can only you have to focus only on what the code of the Lambda function is, because that's the intelligence that your API brings in. And these were just 5 examples. But Lambda is designed to hook up with lots of other AWS services. Amazon Echo Skills Kit, or the Alexa Skills Kit, is the intelligence behind the Echo device. So you could trigger a Lambda function using that Echo Skills Kit, and therefore have interactive voice recognition applications which you can build on top of the Amazon Echo. So instead of the Echo having a standard response, you can say, whenever you speak to an Echo device, or you say, Alexa, what's the time right now? Instead of giving you the standard answer, you can have it customized to give you time in a different time zone, or it could actually respond to your questions in a different way. Today morning, we announced the availability of Lambda scheduled events. So instead of invoking Lambda functions on the occurrence of an event or the presence of some data, you can invoke the Lambda function on a regular schedule. And therefore, you can run a lot of cleanup or batch jobs on top of AWS Lambda. Especially now that the time duration of a Lambda function is 5 minutes, you can actually run ETL applications or your daily query metrics on top of AWS Lambda, because it can run for 5 minutes and run your query for you. IoT actions is another one. We announced that today morning of the whole AWS IoT environment. So every time there is a new data available in the IoT space, you can create an action to trigger the Lambda function. Or many other of these services. SES is another one which we recently announced, where every inbound email can also trigger a Lambda function as an action that you want to do to process that incoming email. So AWS overall is starting to have a lot of these services built in Lambda hooks to allow you to customize the behavior of those services and to run these specific small tasks or even large functions, if you may, of what you want to do to customize the way the service behaves. And that makes it very powerful to get started writing these applications, because as we saw, with just 60 lines of code, if you can write a whole transcoding application, think of how much work it would be just to say, for example, in a CloudFormation resource, I want to attach a second ENI to an instance. That's just going to be 3 lines of code, and all of a sudden you've extended the functionality that CloudFormation offers. So these are the architecture patterns, but let's talk of a few tips and tricks of what different things you could do other than the very standard data processing architecture flows. So let's think of the first one as auditing CloudTrail activity. CloudTrail provides a log of all of the APIs that have been called in your account. Now, while CloudTrail doesn't directly feed into a Lambda function, CloudTrail does output the data to an S3 bucket. And you know that once you have the data in an S3 bucket, you can invoke a Lambda function, and then you could audit that activity. For example, you can run these auditing mechanisms and say, I want to check if each of the APIs actually had a user which had permissions, the right permissions to have those API calls. And if you find somebody who didn't really have the permissions but still managed to do an API call, you want an SNS topic notification to say you want to inform that user to stop calling that API. Or instead of just a notification, you can actually take the whole action right there. You can go and change the configuration policies on AWS IAM and just stop that user from ever calling that API again. Similarly, how you could use Lambda for automated infrastructure management. Amazon CloudWatch also has lots of these alarms that you can set up, and all of the individual instances and all of the infrastructure on Amazon can push to CloudWatch their metrics, and you can set an alarm on those metrics. Now, CloudWatch alarms can go and trigger, can post to an SNS topic. And as you remember, once you have it in an SNS topic, you can invoke a Lambda function, and then you can take some action based on that. So what you can do is you can call the API based on what alarm you saw. So a lot of the alarms, what you often get, are just notifications. And most customers have a standard runbook, which you execute when you find that alarm that's popping up in your inbox. So instead of having that runbook, a manual process, you could quickly automate it using a Lambda function. And it might just be something as simple as spin up a new EC2 instance with some special configuration, which an auto-scaling group wouldn't support. Or you could extend the functionality. For example, an Amazon ECS, the EC2 container service, doesn't have an auto-scaling equivalent functionality yet. But if you want to do something similar, you can go and say ECS start task to spin up a new container inside of your cluster, or any of the other infrastructure management APIs. And we have a blog post. I'm not sure if you could see the link, but we have a blog out there on how you could make this work for you. But then note that this is any API call. It doesn't have to be limited to AWS APIs. So let's talk about a way in which you can use Lambda to forward data to external endpoints by calling out external APIs. So whether you are calling in CloudWatch events, or you have auto-scaling group rules which are getting triggered, as those feed into SNS, you could have that pushed to a Lambda function. And then Lambda can go and publish that outside of AWS, for example, to an IFT via the Maker channel. And again, we have a blog post in a GitHub repo of how you could make this work for you. And this doesn't necessarily have to be IFT. This could be any sort of external endpoint. You could publish it to a Slack channel so that everybody in the team knows what's going on. Or you can even publish it, you can push those events to a private endpoint in your own data center if you want to take some actions in your on-prem environment. The last quick hack I'd like to show is how you could use Lambda functions to deploy Lambda functions. It's Lambda everywhere, all the way down. So GitHub repo has something called hooks. And you can have an SNS topic which responds to those hooks. And as usual, once it's in SNS, it's in Lambda, you do what you want to do with it. And that what you want to do can always be lambda.createFunction. So you can have one master function which you can use to synchronize your GitHub with the AWS Lambda. And now that we have versioning support in AWS Lambda as of today, you can actually synchronize version by version of what's going on. So that every time there's a new repo push to GitHub, you can create a new version of your Lambda function and keep that in sync with your GitHub repo. These are just small tips and tricks, but I'd like to call out a few others. Lambda often reuses the containers that it uses behind the scenes to execute your code. And because the containers are reused, anything that you write to temp can be used as a cache. It won't be a very reliable cache because it's not necessarily you'll always land on the same container. But some of this information you can very quickly cache on the temp space. We have a blog post of how you could use that. We could run arbitrary binaries. The way you saw in my function, I had ffmpeg embedded into my system. That has nothing to do with Lambda. I just embedded it into the same zip file. Similarly, you can embed any other binaries, including things which you have compiled in other languages not supported today. So if you have a Go or a Python 3.5 library which you would like to run in here, you can simply embed the whole binary in here and run it as the way I showed in my Lambda function. We have Grunt and Jenkins plugins, and again, those you can look up of how you could use them. I talked of Slack. We have another blog post of how you could hook up to Slack. You can pass along the event-driven benefits of AWS Lambda to an ECS container. Let's say you have to use Docker in your environment because that's what you're using for your on-premise, and you want your AWS to look the exact same in terms of deployment as your on-premise environment, and use Docker for that. So while you are letting go of the serverless part of it, you can still make use of the event-driven part of Lambda, where any of the event sources triggering a Lambda function, all the Lambda function does is goes and does start task in ECS. And therefore, giving you a very event-driven architecture built right on top of EC2 container service. And we have a blog post of how you could do that. And finally, we have a JAWS framework. We had a talk by them today here. Not sure if you had an opportunity to look at it, but I hope you catch the YouTube video after that. But here's a link out to what their framework looks like, and makes it very easy to deploy and manage API gateway and Lambda functions. So thank you so much for listening in. I hope it was some value to you.